Properties of Cartesian Products, Introduction. So we've been working with Cartesian products, and you've learned how to actually create them, how to find all those ordered pairs. Now, we're going to move beyond just finding them and start looking at how they behave. This slide is an introduction to the properties of Cartesian products. Think of properties as the rules that govern how these products work. Just like numbers have properties, like the commutative property of addition, Cartesian products also have certain characteristics. We're going to explore these properties over the next few slides. Understanding these properties isn't just about memorizing rules, it's about building a really solid understanding of Cartesian products and seeing where and how they can be used in more complex mathematical situations. So, let's dive in and see what makes these products tick. Commutative property. Let's recall some things you already know about set theory. In set theory, many operations are commutative. Commutative simply means that the order in which you perform the operation doesn't change the result. A great example of this is the union of two sets. Here on the slide, we see an example. A union B equals B union A. What that means is, if you combine all the elements of set A with all the elements of set B, you get the same result whether you start with A and add B, or start with B and add A, it doesn't matter. However, and this is a crucial point, the Cartesian product doesn't follow this rule. The Cartesian product is not commutative. This means that, generally speaking, a cross B is not the same as B cross A. Remember, cross is how we say the Cartesian product symbol. Why is this? Well, the Cartesian product creates ordered pairs, and the order within those pairs is important. The ordered pair, a B, is completely different from the ordered pair, B, A, unless A happens to be equal to B. If A and B are different elements, swapping their positions creates a different ordered pair, and therefore a different element in the Cartesian product. So we've just learned what Cartesian products are, how to create those ordered pairs from two sets. Now, we're starting to look at how these products behave, and specifically, whether the order in which we take the sets matters. We'll see this very clearly with an example on the next slide, where we'll actually construct these Cartesian products to demonstrate that the order does indeed matter. So, keep this non-commutative property in mind as we move forward. Commutative property example. So let's solidify our understanding of why the Cartesian product isn't commutative with a concrete example. As we discussed on the previous slide, commutativity means the order doesn't matter, but we suspect that does matter for Cartesian products. Here, we're defining two sets. Set A, which contains the elements 1 and 2, and set B, which contains the elements A and B. Remember, the order within the curly braces doesn't matter for a set itself, but it will matter when we form ordered pairs in the Cartesian product. First, we'll calculate a cross B. This means we take every element from set A and pair it with every element from set B. So we start with 1 and pair it with A, giving us the ordered pair 1, A, then 1 paired with B, giving us 1B. Next, we move to 2 from set A, pairing it with A, resulting in 2 A, and finally 2 paired with B, giving us 2B. Therefore, a cross B is the set containing the ordered pairs 1A, 1B, 2A, and 2B. Now, let's calculate B cross A this time. We take every element from set B and pair it with every element from set A. So, A paired with 1 gives us the ordered pair A1. A paired with 2 gives us A2. Then, B paired with 1 gives us B1, and B paired with 2 gives us B2. Therefore, B cross A is the set containing the ordered pairs A1, A2, B1, and B2. Notice carefully that the set across B, which is 1A, 1B, 2A, 2B, is not the same as the set B cross A, which is A1, A2, B1, B2. The ordered pairs are different. This clearly demonstrates that the Cartesian product is not commutative. The order of the sets absolutely matters. This is a crucial point to remember as we move forward, because understanding this non-commutativity will be important when we apply Cartesian products to more complex problems, as we'll see in the upcoming slides. Commutative property, special case. So let's move on to a special situation regarding the commutative property of Cartesian products. As we discussed on the previous slide, generally, a cross B is not equal to B cross, the order of the sets definitely matters. However, there's one specific instance where they do become equal, and that is when set A is identical to set B. Think about it. If A and B contain exactly the same elements, then swapping their order in the Cartesian product won't change the resulting set of ordered pairs. In this scenario, the Cartesian product simplifies to a cross A. This means we're creating ordered pairs, where both the first and second elements in each pair are drawn from the same set, A. For example, if it is the set containing 1 and 2, then a cross A would be the set of ordered pairs 1, 1, 1, 2, 2, 1, and 2, 2. It's all the possible combinations of elements taken from that single set A paired with themselves. This is an important exception to remember, and it's good to understand why it happens. We'll be building on these concepts as we move forward, especially when we start looking at more complex applications of Cartesian products, so make sure you have a firm grasp of this special case. Size of a Cartesian product. So let's move on to understanding how many elements are in a Cartesian product. As we've just seen with the commutative property, the order of the sets matters when forming the product, but what about the number of elements it contains? This slide tells us that the size, or what mathematicians call the cardinality, of a Cartesian product is directly linked to the sizes of the sets we're multiplying together. Think of it this way. When we create all possible ordered pairs, the number of pairs we get depends on how many choices we have for the first element and how many choices we have for the second. Specifically, if set A has m elements and set B has n elements, then the Cartesian product of A and B across B will have m times n elements. We can express this mathematically as the cardinality of a cross B, written as absolute value of a cross B, is equal to the cardinality of A multiplied by the cardinality of B. Now let's break down that notation. The vertical bars, absolute value, around a set, like absolute value of A, simply represent the number of elements within that set. So, absolute value of A means the number of elements in set A. Therefore, the formula is just a concise way of saying the number of elements in a cross B is equal to the number of elements in A, multiplied by the number of elements in B. This is a really important concept, and we'll solidify it with an example on the next slide. But keep this in mind, it's all about the choices. For each of the m elements in set A, we have n choices in set B, giving us a total of m times n possible ordered pairs. And that's exactly what the Cartesian product represents. Size of a Cartesian product example. Let's solidify our understanding of how to determine the size of a Cartesian product with a concrete example. Here we have two sets. A and B. Set A contains the elements x, y, and z, and set B contains the elements 4 and 5. Now remember from the previous slide, we discussed that the size or cardinality of a set is simply the number of elements it contains. So, if we denote the size of set A as it equals 3 because it has 3 elements, x, y, and z. Similarly, the size of set B, denoted as B, is 2, as B has 2 elements, 4 and 5. Now, applying the property we just learned, the size of the Cartesian product of A and B, written as A times B, is equal to the product of the sizes of A and B. Therefore, A times B is 3 multiplied by 2, which equals 6. This means the Cartesian product A times B should contain 6 ordered pairs. Let's actually list out the elements of A times B to verify this. Remember, the Cartesian product consists of all possible ordered pairs where the first element comes from A and the second element comes from B. So we have x4, x5, y4, y5, z4, and z5. If you count these up, you'll see that there are indeed 6 ordered pairs. This confirms our calculation. The size of A times B is 6, matching what we predicted using the formula. This example reinforces the idea that knowing the sizes of the individual sets allows us to quickly determine the size of their Cartesian product. In the next slide, we'll extend this concept to even more than 2 sets. Generalization of Cartesian product size. So we've been looking at Cartesian products, and we've established how to find them with two sets, and importantly, that the order of the sets does matter. It's not commutative, as we saw on the previous slides. We also figured out how to calculate the number of elements in the Cartesian product when we have two sets. Now, let's take that a step further. This slide shows us that the idea isn't limited to just two sets. We can actually extend this concept to any number of sets. Here, we're saying that if you have a collection of sets, and we're representing them as a subscript 1, a subscript 2, and so on up to a subscript n, then the size of their Cartesian product is found by multiplying the sizes of each of those individual sets together. Let me break that down. The formula shown here, absolute value of a 1 cross a 2 cross a n equals absolute value of a 1 times absolute value of a 2 times absolute value of a n, essentially means this. The number of ordered n tuples, that's just a list of n elements, like an ordered list, in the Cartesian product of these n sets is equal to the product of the number of elements in each set. So, if you had 3 sets, you'd multiply the number of elements in the first set by the number of elements in the second set, and then by the number of elements in the third set. If you had 5 sets, you'd multiply the number of elements in all 5 sets together, and so on. This is a really useful generalization, and it'll come in handy when you start working with more complex mathematical structures. On the next slide, we'll recap everything we've learned about Cartesian products, so make sure you've got a good grasp of this before we move on. Key takeaways. Let's recap the key takeaways from our discussion on Cartesian products. This will help solidify your understanding before we move on. First, and this is really important to remember, the Cartesian product is not commutative. What does that mean? Well, it means that if you have two sets, A and B, the Cartesian product of A and B, which we write as a cross B, is generally not the same as the Cartesian product of B and a B cross A. We demonstrated this with an example earlier, showing that the ordered pairs you get are different depending on the order of the sets. The only exception to this rule is if set A is exactly equal to set B in that special case. A cross B will be the same as B cross A. Next, let's talk about the size of a Cartesian product. If you want to know how many elements are in the Cartesian product of two sets, A and B, you don't add the number of elements in each set. Instead, you multiply them. We represent the number of elements in a set using vertical bars. So, the number of elements in set A is written as the cardinality of A, and the number of elements in set B is the cardinality of B. Therefore, the number of elements in a cross B, the cardinality of a cross B, is equal to the cardinality of a multiplied by the cardinality of B. Finally, this idea isn't limited to just two sets. This principle extends to any number of sets. If you have sets a 1, a 2, all the way up to a n, then the number of elements in their Cartesian product, a 1 cross a 2 cross a n, is simply the product of the number of elements in each individual set. So, you multiply the cardinality of a 1 by the cardinality of a 2, and so on, up to the cardinality of a n. Keep these 3 points in mind, as they form the foundation for working with Cartesian products. In the next slide, we'll address some common mistakes students make when dealing with these concepts, so you can avoid them in your own work. Common mistakes. Now, remember back when we discussed the commutative property? We talked about how, for operations like union, where a union B is the same as B union A, the order didn't matter. However, we specifically established that the Cartesian product isn't like that. A very common mistake is to assume that a cross B is equal to B cross A. This is generally not true. The order of the sets absolutely matters. Think about it. In the ordered pair, the first element comes from the first set, and the second element comes from the second set. Switching the sets switches which element comes from where, creating a completely different ordered pair. Always keep in mind that the order of the elements within the ordered pairs is crucial. It's easy to get tripped up when figuring out how many elements are in the Cartesian product. A lot of students mistakenly add the number of elements in each set. But remember, we learned that if set A has m elements and set B has n elements, then the Cartesian product across B has m times n elements. So, you need to multiply the number of elements in each set to find the total number of ordered pairs. This is a fundamental point. The Cartesian product isn't just a collection of any old elements, it's a collection of ordered pairs, and that ordered part is key. The order within each pair matters significantly. For example, the ordered pair 1, 2 is completely different from 2, 1. So, always remember to express the elements of a Cartesian product as these ordered pairs. Let's move on to the final slide, which highlights some common pitfalls students often encounter when working with Cartesian products. This is really important, so pay close attention. So, keep these common mistakes in mind as you practice, and you'll be well on your way to mastering Cartesian products.